Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be using graphic organizers to classify real numbers. Now, in previous courses, you have learned how to classify real numbers, and you've used the set of natural numbers, whole numbers, integers, and rational numbers. In this course, we're going to add a new subset of irrational numbers. Called irrational numbers. But before we do, let's talk about why we classify things. So, you might have learned that in science, biologists classify animals based on their shared characteristics. For example, a horse is an animal. That's in its broadest sense, an animal. It's also a vertebrate, a mammal, and an equine. The equine is the most specific classification of a horse. Okay, now mathematicians classify numbers based on their shared characteristics. You already know that the set of rational numbers consists of natural numbers, whole numbers, integers, square roots of perfect squares, fractions, and decimals. So the set of real numbers consists of the set of rational numbers and the set of irrational numbers. So let me just highlight this here. So this large box here is the set of real numbers. And all real numbers are composed of either rational numbers or irrational numbers. Now, these are separate because an irrational number can never be rational. Okay? Now, just by way of review, rational numbers are non-repeating, non-terminating decimals. Non-repeating, non-terminating decimals. Rational numbers are numbers that can be written as the ratio of two integers. Any number that can be written as the ratio of two integers is a rational number. Now, what are integers? Integers are all the whole numbers plus their opposites. So example, -3, -2, -1, 0, 1, 2, Okay. Now, what are whole numbers? Whole numbers are the counting numbers beginning with 0. So 0, 1, 2, Natural numbers are just your counting numbers. So natural numbers start with 1, 2, 3, Okay. Now, in example 1, they want us to place the numbers below into the graphic organizer. And we're going to be placing it into its most specific spot. So 25 over 5 would simplify to 5. 25 divided by 5 is 5. So that is a counting number. So we're going to put, I should have written it like this. We're going to put 25 over 5 would be a natural number. 25 over 5 would go in the natural number category. Now, square root 32. Now, I've got my calculator ready over here. If I put square root of 32 in my calculator, we get 5.6568. It goes on forever. So anything that's non-repeating, non-terminating decimal has to be irrational. So square root 32 would go over here in the irrational numbers. It cannot go on the rational number side. All right? Now 0. The first place we see 0 occur is in whole numbers. Okay? That means 0 is a whole number, an integer, and a rational number. Okay? -12.2. Now, -12.2 is a terminating decimal. So that would go in the rational number category. Square root of 225. So let's look at that. Square root 225. And that reduces to a whole number. Well, in fact, it reduces to a natural number. So I'm going to put square root 225 in my natural number because it's a counting number. Okay, our next number, negative 0.625, that is a terminating decimal. So that would go in our rational numbers. Now pi, if I put pi in my calculator, see how it goes on forever and ever and ever? It never terminates, nor does it repeat. So pi would be an example of an irrational number. All right, negative 24 divided by 3 would be negative 8. So it's not a counting number, it's not natural, it's not a whole number, but it is an integer, negative 24 over 3. The whole numbers plus their opposites. All right, 1/3. That is the ratio of two integers, so I'm going to put 1/3 in the rational number category. Now, next one, negative square root of 81 would be negative 9, so that would go in my integer category because it simplifies to negative 9. All right, example 2. If possible, give an example for each of the following. All right, we want an irrational number with a value greater than 10. So an irrational number needs to be a non-repeating or non-terminating decimal. So I'm going to use a square root. And we know the square root of 100 is 10, so I need something bigger than 100. So maybe something like square root of 110. There's lots of answers you could put here. Square root of 110. And let me just show you that that does indeed work out to an irrational number with a great value greater than 10. See 10.48808848817. All right. Problem B, an integer between negative 5 and negative 4. Now let me draw a little number line here for you. Here's negative 5. Here's negative 4. Is there an integer between those two numbers? No. So this is not possible because all the numbers between negative 5 and negative 4 are decimals. Okay. Problem C, a whole number less than 0. Now look at our chart up here. Whole numbers begin with 0. So it is not possible to have a whole number that's less than 0. D, a rational number represented as a square root. All right, so I need a square root, and it needs to be a rational number. So the only way we can find get a square root that's a rational number is if the radicand is a perfect square. So anything you put under here, just make sure it's a perfect square. So say square root 64. Because that would, if I put square root 64 in my calculator, that would give me 8. So that 8 is a rational number. All right, example 3. Classify the given value in the table by checking all that apply. All right, so our first value is 36 over 6, which simplifies simply to 6. So is 6 a natural number? Yes, it's part of the counting numbers. Now, every natural number is also a whole number, an integer, and an irrational number. A rational number. But it is not irrational. Now, all rational numbers are real. So I would check this box too. In fact, all the numbers we're going to do today are real. Believe it or not, in later courses you will study numbers that are non-real numbers. But that's for another day. All right, problem B, square root 23. Now, the square root of 23, do you see that it is a non-repeating, non-terminating decimal? So it must be irrational only. And if it's irrational, it can't be natural, whole, integer, or rational. All right, 0. 0 is a whole number, which means it is also an integer, which means it's also rational, but it cannot be irrational. Okay. 5.45 repeating. Now remember, decimals that repeat are rational numbers. They are not irrational. Okay. Negative square root 144. Now that reduces to negative 12. So it's not a natural number and it's not a whole number because whole numbers begin with 0 and it is an integer. Now all integers are also rational, but they are not irrational. Okay, so I'll put little X's here. You don't have to do this because it said check, but I'll go ahead and do that. All right, example 4. Which set of the following visual representations correctly displays a relationship between the set of real numbers? Now let's look at A. We have the largest set is real. Then we have rationals being a subset of the real numbers, which is true. And then they have irrational being a subset of the rationals, which is not true. An irrational can never be rational. An irrational number cannot be an irrational number. All right. Answer B. We have the set of irrational is the large set. And then we have rational numbers to be a subset of irrational? No way. Irrationals are never a subset of rationals. All right. Problem C. We have the subset of rational. We have a Venn diagram, real and irrational. Okay. The only problem is they have irrational overlapping with the rational, and there's no way an irrational number can ever be irrational. So let's look at D just to make sure. We have the set of real numbers, and then we have the rational is a subset, which is true, and irrational is also a subset, and they are separated. So this is our correct answer. All right. In example 5, set Q and Z are subsets of the real number system. And it says that set Q is rational and set Z are integers. So let's just think about this real quick. Remember, in our real number system, let's look back here. Rational numbers was our big category, and integers is a subset of this. So I need something where rational is the big subset and integers is a smaller subset. Okay. Now in this problem, rational numbers is represented by Q and integers is represented by Z. So I want the big category to be Q, which means I can automatically get rid of answer A. All right. Let's look at answer B. We have the set of real numbers, that's our big set, and then we have the set of rational numbers overlapping the set of integers because some integers are not rational. Well, that's not true. All integers are rational numbers. All right. So let's look at problem C. We have real numbers. Then we have Q, which are the rational numbers. And then we have Z, which are the integers. Because all integers, let me highlight this, all integers are rational numbers. And that is true. So we're going to go with answer choice C. All right, that concludes today's lesson on classifying real numbers.